In this video, we'll cover nonparametric tests of significance, specifically a two-way chi-square test and the median test. Nonparametric tests of significance can be used for data at any level of measurement, but is generally used when we have nominal or ordinal level data. For this video, I will go over an example of the median test because in the course of performing a median test, we actually calculate a two-way chi-square. I will use question 24 from the textbook as an example, which states, two samples of students were asked to read and then evaluate a short story written by a new author. One half of the students were told that the author was a woman, group X1, and the other half were told that the author was a man, group X2. The following evaluations were obtained, higher scores indicating more favorable evaluations, and the data is here. For this data, we could perform a t-test, as it appears to be more or less interval level data. In the case of a t-test, our research hypothesis would be that the population mean evaluations differ between the two groups. For a median test, our research hypothesis is that the population medians differ between the two groups. Therefore, our null hypothesis, which is what we test with our chi-square test, is that the population medians are identical. The first step in performing a median test is to determine the overall median of the data. So I'm going to copy the individual scores for each group into one long column so that I can find its median. To do this, I'll select each column and then copy using Control-C and then paste into this column. Next, I'll label each of these so that it's easier to locate the position of the median. And as you can see, we have 32 observations. The next step is to sort our data. So I'll highlight our observations, select sort and filter, and I'll sort from largest to smallest. Either way is fine. Next, I want to determine the position of the median, which, if you recall from an earlier video, is equal to, in parentheses, our n, in this case 32, plus 1 divided by 2. So our median is between the 16th and 17th observation. In this case, it's the average of 5 and 5, so our median in this case is 5. Now, since we have a list of numbers, we can actually use Excel's median function to determine the median as well. If we select Insert Function and Median, and select all of our numbers, you'll notice that it also gives us the result of 5. In any case, we now know our median, and so we can go to the next step, which is to create a table that shows how many observations in each group are above the median and how many observations are below the median. So I've made a 2x2 table with the columns being each group and the rows being whether it is above the median or not above the median. If there's an observation of 5, it would fall into this group, since it is equal to and not above. To determine the values in each cell, I simply look at each set of data and count how many observations are above the median and how many are at or below the median. In the first group, there are 4 6s, which is above the median, and then the remaining 12 observations are at or below the median. For group X2, I have 5 observations of 8, as well as 4 observations of 6, which equals 9 observations above the median, and then the remaining 7 are at or below the median. At this point, I have a cross tabulation, a table of numbers or observations based on 2 variables, so I can perform a chi-square test. Chi-square tests require us to know the marginals, that is, both the column and row totals. So next, I will sum each row and column. I select the function sum, and the 2 cells containing observations for group X1. Copy that over to X2. And do the same for the rows. So, of the 32 total cases, which are divided equally between each of the 2 groups, there are 13 observations or evaluations that are above the median and 19 observations that are at or below the median. So now we're ready to perform a chi-square test. Here's the formula for chi-square. It only requires 2 variables, f sub o and f sub e, which are our observed frequencies, which are the entries in our table, and our expected frequencies. The expected frequency for any cell is equal to the row marginal total times the column marginal total divided by n. Here I've constructed a table in order to calculate my chi-square statistic. Each row in the table corresponds to 1 cell in my crosstab. So UL is the upper left cell, UR is the upper right cell, LL is the lower left cell, and LR is the lower right cell. You can label these in your table however you'd like. First, for our observed frequencies, we simply copy the values from our crosstab. Next, we calculate expected frequencies. The expected frequency is the frequency we would expect if the group designation did not matter. For the upper left cell, this is equal to, in parentheses, the row total for the row that contains the cell, in this case 13, times the column total for the column that contains the cell, or 16, close parentheses, divided by the total number of observations. Note, if the group you belong to doesn't matter, and there are an equal number of cases in each group, you would expect the 13 cases above the median to be equally distributed between the 2 groups. And in fact, 6.5 is 1/2 of the row total. Using the formula is preferable in that sometimes there are not equal numbers of cases in each group, and the formula takes unequal cases into account as well. For the upper right cell, we do the same procedure. It is equal to, parentheses, the row total for the upper right cell of 9, which again is 13, times the column total for that cell, which is 16, close parentheses, divided by the total sample size. And again, we have an expected frequency of 6.5. For the lower left cell, which is 12, our expected frequency is the row total, or 19, times the column total, or 16, divided by 32. or 9.5. And similarly, for the lower right cell, which has 7 observations, is equal to 19 times 16 divided by 32. One way to check whether you've calculated your expected frequencies correctly is to look at the sum. You'll notice that the sum of the expected frequency is equal to the total n. This should always be the case. The expected frequency tells us how many observations we should see in each cell, given that we have a sample size of n and the marginal totals. So now we have our two variables, and we can calculate our chi-square. Here's our chi-square formula. The first thing we want to do is to determine the difference between the expected frequency and our observed frequencies. So I've created a column for that, and each cell in that column is equal to the observed frequency minus the expected frequency. I can then copy that into the remaining cells. The difference between the observed and expected frequency is essentially a deviation score. And if you recall from our measures of variability chapter, when you sum all the deviation scores, you should get a sum of 0. And if you sum these four, you'll see that that's the case. Next, we square that deviation. So I type equals the difference squared. Finally, to complete this term, we divide each squared deviation by its expected frequency. So I type equals squared deviation for the row divided by its expected frequency. And then I can copy that to the rest of the cells. Our chi-square statistic is simply the sum of all those squared deviations divided by their expected frequencies. So in this case, I obtain a chi-square value of 3.2389. Just as with other tests of significance, once we calculate our statistic, we compare it to a critical value for that statistic given our degrees of freedom. The formula for degrees of freedom for a chi-square or median test is simply the number of rows in our table minus 1 times the number of columns in our table minus 1. Here's our table. You'll note it has 2 rows above the median and not above the median, and 2 columns, x1 and x2. So our degrees of freedom is equal to 2 minus 1 times 2 minus 1, or 1 times 1, or 1. We can now look up a critical chi-squared value from the table in the textbook. That table can be found on page 474. It's table E, which is critical values of chi-square at the 0.05 and 0.01 levels of significance. We'll use a 0.05 level of significance, and we see for 1 degree of freedom, the critical value is 3.841. Since our calculated chi-square 3.24 is lower than our critical value, we retain the null hypothesis. In other words, it is possible that there is no difference in evaluations by students when told that the author of a written piece is a man versus a woman. However, I actually performed this chi-square test incorrectly. This is the formula for chi-square, but there are certain instances in which we want to add a correction to the formula. This correction specifically applies to 2 by 2 tables, that is, tables with 2 rows and 2 columns, as we have here, when we have fewer than 10 observations in any given cell. You'll notice that 3 of our 4 cells meet that criteria. And so we should apply this correction, which is called Yate's correction. Here's the formula for Yate's correction. Essentially, we discount each deviation by 0.5 before we square it. This ensures that our chi-square is not unreasonably inflated by low observed frequencies. Since we want the size of the deviation to be 0.5 smaller, regardless of its sign, we have to incorporate an absolute value as well. So, here's a new table that I've constructed to include the steps needed to perform a Yate's correction on our data. Our observed and expected frequencies are the same, therefore our deviation scores are the same, but then we need to alter our calculations. The first thing we'll do after calculating a deviation score is to take its absolute value, which means we get rid of any negative signs. You can do this by hand or by using the Excel function ABS and selecting the appropriate cell. Notice it converted negative 2.5 into 2.5. Next, we discount each of those deviation scores by 0.5. So I type equals the absolute value of the deviation minus 0.5 and copy that into the remaining cells. I then square that and then divide each of those by their respective expected frequencies. So for the first row, representing the upper left cell of our crosstab, this is equal to 4 divided by 6.5. And copy that into the remaining cells. Finally, I sum those scores, which gives me a calculated chi-square of 2.07. Notice this is smaller than the calculated chi-square from our previous example. This is the point of Yate's correction. It produces a more conservative test statistic. Since our larger chi-square did not meet the criteria at the 0.05 level of significance, clearly our new lower calculated chi-square does not either, and so our decision is still to retain the null hypothesis. That is, there is no difference in evaluations based on the sex of the author.